Okay, thank you very much, and happy to see some of the friends in this course, which I hope I will be able to enlighten them in something new, some new results that we have done. So if I may add something about the presentation that Mark so nicely has done, is I'm myself a physicist, a nuclear physicist, but I've been working in archaeology, excavating and having some also excavation in collaboration with archaeologists for many years. And all my projects actually start in the field. So I do work hard in the field together with the archaeologists in the hard weather. So let me share the screen so that we can start. Share the screen, this one. Okay. So do you see the screen? Is everything okay? Yeah, no.
It's okay, Lisa.
It's okay. Okay. Yeah, you see the screen. So radiocarbon dating. This is a part of the archaeological research, which I assume that most of the archaeologists are more or less familiar, because from when radiocarbon dating was invented, it has become a part of every excavation. I would say at least excavation that are in the 50,000 years range for that. So the talk that I will give today and next Saturday will be divided. And I hope, I mean, I plan to give, you know, not just the basic of radiocarbon, but in particular, some application for radiocarbon and how things are changed and what is the contribution that I have added in this field. And this contribution is not only from the side of method and technique, but also from the archaeological point of view, really field work. And there will be examples that include, you see, historical period, which normally radiocarbon is not used so much in the historical period, because very often we think we have dates, we have documents, we have other methods for putting the events in time. Prehistory, which is more dependent from radiocarbon very often, because it is as less a proxy to be used. But on the other side, in prehistory, there is also more attention or more interest in for the climate as an input in the changes along the human career. I think an aspect is about that normally is not asked very clearly and not developed very in detail, is the real dating question that with radiocarbon or with any dating method is of interest to be answered. And the dating question is very important because it's not born after the excavation. It should be, in a way, you know, being developed during the excavation. And so while we are excavating, to build a strategy to sample for the chronology, not after, when we know what we have found, what we have in our hand, but during the excavation. I will give some recent development in radiocarbon, which regard new materials, new approaches for the radiocarbon dating, some methodology, which has opened a different set of samples and also of questions, and also, of course, calibration and modeling. The sequence of the presentation is not as strict as it is here, but I will try to keep it as much as possible, but things will be more fluid. And at the end of the talk, I hope that I'm happy if there are questions. And then there will be a few case studies. One is in historical periods where radiocarbon and its precision is challenged by historical dates. Paleoclimate studies, okay, and the fact that the possibility that you can date directly the proxy of the climate. You can date directly the archaeological record, and then you can merge the two chronologies together and see, for example, the relation between a cause and effect, if the climate has indeed changed, has induced these changes. And then the arrival of the Homo sapiens in Eurasia as Israel, where much of my work is done. And this was an excavation that I had in collaboration with an archaeologist, Omri Barzilai, from the Israel Antiquity Authority. So this arrival is, for the moment, is the earliest evidence is here in Israel. So radiocarbon is indeed, its first application was indeed dating, was not as a tracer for atmospheric processes, which develop later on. But the first application, of course, is dating, because until this method was not invented, there was no way that we could put any of the archaeological record in absolute time. There was a lot of assumption. Sorry. There were a lot of relative chronology that helped to build the chronology of the different sites. And this was, the first evidence that radiocarbon is indeed a dating method with historical dates on this axis. And here was the content of C14. And you see that on the decay law, we have exactly the radiocarbon dates. It was a very nice application. And Libby got his Nobel Prize, but not only for archaeology. As you see, was mentioned for geology, geophysics, and other branches of science. It's really very widely applicated radiocarbon, not only for archaeology. But I think that archaeology is the major application for radiocarbon. So Nobel Prize in the 60s. Actually, archaeology is indeed much more, I would say, emotional, can raise a lot of emotion, because you see, when you have a context like this one from, for example, Tel Safi, you have a room which is abandoned, and it is abandoned thousands and thousands of years ago. You still see, the jar there on the floor, the other container here, you see the ash layer here. So people can see as a windows in the past, and this is very nice. And that's why archaeology is of large interest for the public. And as I say, raise emotion, because you see a connection with the past, and this is nice, it's beautiful, but it is a lot of work. And from this to get to real information and understand the past life and what happened thousands and thousands of years ago is a lot of hard work and thinking and analysis and modeling and so on. So, but indeed, it is beautiful in this respect, archaeology, better than a laboratory where I work, and people get less excited to see a centrifuge than to see a jar like that. But so I think that in archaeology, the methodology for the excavation has developed a lot along the development of this discipline, archaeology. So you have, you know, from just taking material out of the ground, you know, you have area, square, locus, features. Every excavation has some particular definition of the uncovering of the different of the past. You have, you know, images and drawing and building the database, which now with a lot of computer and imaging has given now a lot of advancement in recording while you are excavating and moving, taking away the record. And then when you have to build up the understanding of the past, so there is a real very, very big advancement in this respect. And the major, you know, the major items is pottery or lithics, let's say, that they are the one that define the cultural and the cultural changes. You see this material that is not, doesn't remain the same, develop, evolve, and based on that, relative chronology was also built. And when the recovering of all the material is done, there are different methods. So you can sieve, you can wet sieving with flotation, you can collect in the field. And so there are, but this is dictated also, the mode is dictated also from the nature of the site. If it is from the environment and so on. And you have discipline, which are very often associated in the excavation. You have an archaeobotanist that is there during the excavation, collecting charred remains or uncharred seeds, wood for later analysis and understanding what the environment is. Archaeozoologists that see the bones, so you know, agriculture or animal management, food. You have the anthropologist, which now is not only recovering the bones and see if there are burials for the humans, but also the ancient DNA is now very much included in the research. But chronology, you know, it's very rare that I see a chronologist associated in an excavation. Sometimes he comes for one day just to see the site, understand the stratigraphy, but a chronologist that follow up the stratigraphy, follow up the excavation, excavate the context and the site, I think I never seen one like that, or is very, very seldom. Normally, chronology, you know, you excavate, then you analyze all your remains during the between one season and the other. You get a better understanding of the stratigraphy or what you have seen, and then it is decided by also what has been found in archaeobotany, archaeozoology, or in anthropology to take some of the samples that were recovered and maybe use it for dating, because for C14 is normally, you know, is bone, the material, and charred botanical remains. These are the two major samples that are used for C14. There are others, but these are the major ones. But the chronology question is in general developed after it is seen what is in our end as material for dating and stratigraphy. But my approach is different, and it's because once it is excavated, the material, then you cannot go back. You can say, oh, I should have collected this or that, or recorded, or check, and so on. So that's why being in the excavation preserve us, you know, that just one date is not data. And I say that because once the material is collected, you have already lost what maybe was the best date. But why do I say that? You will see, because in many archaeological sites, you don't find what you want. You find what is left. You find what is what has survived there, and you have in a way to cope with what has been lost. And that's why on the top of what is lost during time, the excavation, if the chronological question is not accompanying the excavation together, is sometimes is difficult to be answered. So, but one day is no data is a saying, which is true, except in very few cases, like for example, if you find a basket like this one in the desert, here in Israel has been found in a cave, a full, complete basket, huge, it's really big. I can enter this basket. It can contain my person. So, and when I dated, it came out to be 10,000 years old. That's, is an amazing discovery, is beautiful, is certainly important in understanding the technology of basketry, what the people did maybe in the cave with this huge basket. And in this case, the date is the date of the object, and is one date. It is a date in this case. But these are very specific, very rare. More often, and I think is even more with larger implication, is when you have an excavation and you really rebuild that site through the thousands and thousands of years. And here I show you the radiocarbon. That's most probably you have already seen. So this is with the new calibration curve in 2020. So this is the radiocarbon measurement. The red Gaussian is the calculated radiocarbon date based on the concentration of C14. And then through the calibration, this beautiful Gaussian is transformed in a probability distribution that the calibration, depending how it is articulated, then you have a larger or smaller range of what we say is the calibrated range, the time that we can use for synchronizing the event. So most of the archaeology is indeed, a tale, is a site, and here we have the relative chronology based on stratigraphy that is familiar to the archaeologist, and it is indeed, with the time this is built as a time in time relation. The bottom one, the layers at the bottom should be older than the layer on the top. But together with the layers, you can find the pottery, and the pottery has an evolution. So you can build some relation with the cultural periods according to the region, according to the site. Even in the same site, you can correlate by pottery the different layers. This is a type of dating. The problem, and there are problems with this type of relative dating, is that as there are more and more excavations, as there are more and more remains found, the questions that are asked related to the time become more and more challenging. It's not only to know if you are in the Iron Age 2, Iron Age 1, or late Bronze, but really if the late Bronze and Iron Age, for example, transition is related also, for example, to the climate change. or if a site has a pottery which is earlier than a sites in the close by region. So as much as we proceed with this, we become more and more curious, and we want to gain in precision and accuracy with our chronology. And we know very well long discussion about some events like the Santorini eruption, which is still going on as the proxy used for dating these events present some inconsistencies in the interpretation. So, you know, we excavate, we uncover the walls, we leave some of the architecture standing until it becomes floating. We describe the different layers in the sequence of the excavation, and we can even correlate one part of the excavation with maybe another part of the excavation by having the same pottery. Now, the question now that we can ask with C14 is the transition. When you are in the full of your period, everything is you know where you are. But the transition timing, this transition or this transition or this transition, that's sometimes a major effort in chronology, and also for a major challenge for radiocarbon. For example, if you take the late Bronze to Iron Age transition in the southern Levant, which is marked by the arrival of the sea people, of the Goyim, so the sea people with this population that invaded the south of the Levant and Egypt. And, you know, if you take the relative chronology and you color the different layers for sites like Kubur el-Baladia, which is here, Ashkelon, Tel el-Safi, Megiddo, you color the layers for this transition, for this change. And then if you have absolute data for those layers, then you can synchronize the transition when, for example, the Philistine one appeared in the southern Levant, and then you can see if you know your LB period is end earlier than in other sites according to the C14. And as you see here in this plot, which is based on C14, the lines are not straight, are not just a line like this. Because C14, as you've seen in this plot, you know, here, it has a range. It's not one number. It's not a 10,500 or 10,400. It's a range of possibility. And when we get on very specific dates, then we have this uncertainty, and that's why we have this oblique line, just to indicate that C14 has a probability. It could be from here to here, okay? So this is to get real now, to get to the core of the question. And because this transition between the LB and the Iron Age here is marked in the southern Levant and also in the northern Levant by a change. In this case, the plot is based on the olive pollen here. On the olive pollen, you see that there is in the northern Levant a drastic change, and also in the south Levant we have a decrease in pollen from the olive. Then it is related to a climate change. Now, is this a climate change detected here and here by this proxy, synchronized with the arrival of the sea people? Like, was the climate change a cause for it, or was it just happening by itself, and the sea people arrive in the southern Levant for different reasons? And this is, you know, the time scale is the same. Time is the same. When was the year 1100 in the southern Levant? Was the year 1100 in the Aegean, in Turkey, and in Egypt? But the resolution that we have here in the archaeological record should be comparable to the resolution here. It is here. It is 1100 between here and here. No, this is like a zoom in this case. So is the resolution in this record that determine the change in climate sufficient or comparable to the resolution we have in the archaeological record based on pottery remains? And is radiocarbon sufficient for that? Able to synchronize this time with this time, or this, the end of this with here? Is it sufficient? Or now that we understand the question, if this is the question that I want to answer by radiocarbon and by the chronology, then yes, I date many sites, and not just one site. I date many sites. I first check that typologically we are synchronized, because if we are not synchronized typologically, then we can argue if the climate is not the reason for the change in that I detect in pottery, and I say, oh, these new people arrived. If this is not if this change is not synchronized in itself, then the question with the climate is maybe is not related to that. So that's why I'm saying building a chronology is really understanding the question I want to answer by the site that I have, or the sites I have available for this question, and build up the not only what should date it, the seeds because it's a short-lived, or bones that is a short-lived, but how many samples. I should date all the different layers that I can detect in the site to really see the sequence of the dates, not only a date here and the date here and the date here. But really build the density of the dates according to the question I want to answer. And that's you know, what is my approach in a sense. What I think is radiocarbon can give much more input in archaeology and be much more useful and enlight the chronology if this is done first of all in the field. So and that's for the next question, you know, you have already the answer, because one can say, well, sometimes you can ask, is radiocarbon, the sensitivity, the precision good enough for this question? Like if I want to know 1 year event or when one specific king went in power, maybe radiocarbon is really, maybe we have to wait a little bit more years when we will have a super good calibration curve. But more often is the question and the possibility to answer with C14 more related to the sample density I have, and the archaeological context that I have available. But sometimes the archaeological context, you have to create it for the chronology. It doesn't have to be the beautiful jar as we saw in the very beginning, you know, that this is visible and is recognizable, but maybe there is nothing to date inside the jar. More often, the archaeological context for the chronology is more invisible, and you need some other instrumentation to find out. That's what we have developed for this along the studies. something which is related to the southern and northern Levant, the black wheel made ware, which as a pottery is a peg, is a link between the southern and the northern Levant, in the middle of the, now we go to the name, to the EB4, as we call it in the southern, or IBA in the southern Levant. And then you have the EB4A and EB4B in the northern Levant. This black wheel made ware is found in the northern Levant, has been found here in several sites, and has been associated to that specific period. Okay, so with other reasoning, some of these layers has been how do you say, associated to some specific period. Here we have the time BCE. In some cases, like in Tel Arqa, Fadus, and Umbashi, reading the report, the black wheel made ware was found in some layers, and those layers were dated. So then we have the C14 dates, and you see they may cover very large range, even to certain, to our understanding, even an impossible situation to be so early for this pottery. Or Tel Arqa, which is those pottery were late. So this brings me back to the question: is this this overlap or this very wide range of possibility is due to radiocarbon in the case of these sites, or is due to the archaeological record, which is, is complicated? There can be movement, there can be intrusiveness of sediments between layers, removal of layers, and so on and so forth. So it's harder to believe that if the radiocarbon of this site was supposed to be here, there is such a big mistake in radiocarbon. Okay. But certainly the chronology for this black wheel made ware is complicated. And in this paper that we have done last year, so we found a black wheel made ware in 4 different sites in the north of Israel, and we have absolutely dated this, and we will see the example of that later on. So what does it mean when we excavated these sites with the idea to date the black wheel made ware? The density of how we look for samples that will date specifically those elements, those context. So radiocarbon, you can say, well, but maybe it's a real problem of radiocarbon. It's so complicated. Radiocarbon, forming the atmosphere with the neutrons that get included in the nitrogen. Then we have the C14. If it forms CO2, it is included in the tree. And we think that everything, is in equilibrium in this system. And indeed it is, because radiocarbon has been forming for billions of years in our atmosphere. And now what is formed also decays. So it is constant in the atmosphere. It is distributed because it's a gas. Initially, it distributed everywhere in the world, and the dates from the south hemisphere to the northern hemisphere in different parts of the world are indeed consistent with this hypothesis. It's a common element, so we have many samples that can be dated. It has an half-life 5,730, which is very suitable to detect fast changes in the archaeology or in the history closer to us. So we can really, again, with that insensitivity. And one big question, and this is more in the part of the chemistry, is if it is a closed system, like once the leaves, the bone, the seed is in the ground, it doesn't exchange with the rest of the environment, including, again, more C14 or carbon. This is another assumption which has been studied. And this is part of the chemistry of the preparation of the samples. So it's more in the lab, the problem. But still you have to understand where the samples was buried to understand against what kind of contamination you have to be worried about. And then because when we talk about the sensitivity, and we have all these, you know, kind of assumption like equilibrium, homogeneously distributed, it is an assumption. It is very much preserved and respected, this assumption, yet there are exceptions. The equilibrium, for example, the fact that it is constant, we know that it's not constant C14 in the atmosphere. That's why we use the dendrochronology, and we build the calibration curve to exactly see what was the radiocarbon content up to 50,000 years ago. Not only dendrochronology, we have other archives that has been used and applied, but dendrochronology is the one that has for the short range archaeology, like for the past 12, 13,000 years, as the best resolution. You have seen the other lecture of Otto Cichocki, if I pronounce correctly, and is the dendrochronologist, is a great researcher. And for C14, we have used the knowledge of dendrochronology to build, based on the sequence of rings and the overlap of the same sequence in trees that help us to go back in the past. So to see the radiocarbon content in the past, because it changed. It changed for the climate, it changed because of the solar activity, it changed because of the geomagnetic field. These are processes that are that have an effect and are known. There is still a lot to do. Always there are more and more information that we obtain from these changes. And as I say before, the more we understand and the more we refine our ability to measure more precisely and accurately the data, the age of a sample, the more difficult question we are pushed to ask. It is a never-ending story, and I think that's what science is. A researcher and is keeping us working with in this field. The calibration curve has changed through time. I would say not dramatically, in the sense, you know, you don't move by 1,000 years, one period or another, but you refine, you extend the limit of the calibration. For example, in 1998, it was 24,000. Today, we got to 55,000. So this is the last 2020 calibration curve, and it is up to 55,000 years. Maybe soon we will get to 60,000. So we are changing, and of course, you say, okay, if I measure my sample in 2009 and I calibrated in 2009, you can still use your measurement of C14, what you have obtained from the laboratory, but you should recalibrate your sample with the updated calibration curve. So the measurement is still valid, but your but you have to recalibrate. And this is important because for some chronologies, sometimes the 100 years, 50 years change might be now important and interesting. So this is the new calibration curve. As you see, goes from, not from 0, but this is 55,000 years here. And the major change in this 2020 is indeed in this part of the calibration curve, some important changes. Here we will see some changes. Now, the calibration curve is useful, is essential. We can't do without that, but it is sometimes a very complicated curve. It's not a straight line. We would like to have a simple straight line so that you can easily measure your C14 and have from your Gaussian obtain here another Gaussian with the most probable date here. Fortunately, it's not. You have this plateau, for example, you have wiggles, which are important information for the past climate or geomagnetic field, solar activity, but for chronology is a pain, is really difficult. But you will see an example. If you have a great sequence of levels in your archaeological sites and you have good samples, then if you are able to, if you have the opportunity to have samples that can follow by stratigraphy this wiggle matching, then you can wiggle matching your stratigraphy with the wiggle. So instead to be a problem, because you can, if you have your data here, you cross here, you cross here, and you will have a large distribution by having other samples before or after in stratigraphic sequence. Then of course you will be able to exclude this part of the calibrated range for these dates. So sometimes if you fall in a wiggle like that, and you know, because you more or less know, if you know more or less that you are in this part of the calibration curve, that's what I'm saying. You have to build your strategy for the chronology. So you will have really to excavate and look for as many good in situ context, because you know that this is your fight for the chronology, and you have to build up the strategy to sample this material. So here is another example. Even if you have normally plus minus 20, 23, which that's a standard radiocarbon date for more or less today measurement, depending from the size of the sample. But in general, you know, if you have your milligram of carbon, then more or less plus minus 20, you have your chronology. And it depends where you fall in the calibration curve. You can be in a nice period like this one, but you can be also in this bad period like this one. So that's a part of your information that you must have ahead in order to build exactly the strategy for the sampling. Something that is very interesting and came out in the last few years is the single here calibration curve. Normally the calibration curve, this one, is putting together 10, 23 ring, and they are put together and dated. So you average those 10, 20 years are averaged in for the calibration curve. Okay, and this is has been useful But now that the questions are becoming more and more important, and we have detected, there was a beautiful study by Yoki, the Japanese researcher, found an excursion of C14, and by measuring single 3 rings in one of these important wiggle, and this has initiated a huge work for single now ear calibration. Here you have the period of between the 1700 BC to 1500 BC is the period of Santorini eruption. You have this is the 2013 calibration curve, the blue line. Here you see the blue line. And they've been measuring, you see all the purple dot, red dot, and gray dot. These are single ear radiocarbon determination in this sequence of about 200 years, 203 rings. It's an incredible amount of work. And you see that more or less the purple, the red, the gray, they do follow the same pattern, except in some case, like this one, for example. And you have another effect here. So now these are important points because this could raise some question about the red point are juniper from the Near East. And if this is raising the question, if in some periods or for some particular event, there is a difference between the general calibration curve all around the world. You see Irish oak and Bristol Compine. These are 2 different regions in the world that seems to be overlapping for the C14, most in the large part of the case. But now you see that there might be some effect. And this is very important because for some event, let's say the Santorini or some chronology, this could be super, super important. And even more important in this case of Santorini is that with this new calibration, this single ear, as you see that this part of the curve, became very similar to this one. There is like a larger and more evident plateau, so that if your event was it here or was it here, maybe with radiocarbon you wouldn't be able to distinguish if you have only one date, like a cluster of seeds, of charged seeds, that will not give you a precise, will give you an answer, but you wouldn't be able to distinguish this point from this point. So that's, another good point to build your strategy. If this is the question you have to answer, that when you excavate, it's not so much the cluster of seeds that you're looking for, but many layers, so that you may be able to follow maybe this curve. If you have many layers, if you have a tree, then you can do wiggle matching, then maybe you can figure out where you are for this question. But this is a development which is now gain more and more interest in the radiocarbon community, because not only for chronology, but also to find what are the reasons for maybe this type of effect that needs to be confirmed, but these are important points. And this is another example of this. You see here you have the blue calibration curve. You see here the blue line of the calibration, the general calibration curve. You have the black is, you know, the point for the calibration curve. You see they have many years put it together. And then you have all the single year that has been measured among those, in all those rings. And you see that the calibration may change in some point, but not dramatically. But of course, it will start to raise a question if this wiggle shouldn't be deeper, for example. So there is a lot of work going on, but this should not make, you shouldn't think, oh, I waited for the best calibration curve and then I start to date, because it's working in progress. And as I say, you can date your sample is today and build your hypothesis and conclusion. And then in 10 years time, reuse that date in the new calibration curve and see if there have been some changes. So this, you know, is it keeps working and the discussion open. So these are here. I thought that we can stop for a question, but let's go on. Okay, let me introduce a concept that I did understand, I did build while I was excavating in the different sites where I was studying the chronology, is the dating assemblage. Like you have a pottery assemblage, a lithic assemblage, you also have a dating assemblage. What does it mean, an assemblage? Well, for dating, you are looking for a sample that had to be still in its original location when it was used by the person, by the human in that time. Like if I think about a charred seeds, these seeds that has been charred for some reason, okay, I would like to find them not dispersed in a bucket of sediments that or in that is related to a 5 centimeter thick or 10 centimeter thick floor or surface, because there is a flat ceramic on it. I would like to find, even if it is only one seed, I want to find it where it was burnt, like in the fireplace. Now a fireplace is big, is small, and I'm showing you here a picture of a context. It was a meter by 1 meter excavation that we did for the EB chronology, and we found this. You see, this is a small layer, very small patch, maybe continue inside, I don't know. But this patch of white and black material. And if you remove, you break it, you see, you know, you have your charred, some are seeds, some are charcoal. You have your black, white material here. And so, you know, we pay attention to this context because when we see that, we don't take the whole system, the whole context in a bucket and we sieve in order to find the forces for data. No, when we excavate for the chronology, then we check the base of this context here. We isolate a chunk of the white to look under the microscope. We collect in the field if we see the seeds and not by sieving, which may break even those few seeds that are there. And we check also the material outside the context to see what is the difference between here, that I don't have the context, and here, the signal. And what are the signal I'm looking for? Well, the signal I'm looking for this context, which is definitely nothing to be, you know, it's not something that surprise or would be even noticed by normally the volunteers in the excavation. It's because we are looking for, you know, if it is a burnt event, still there, if they made here the fire, we have to find the charred remains, we have it. We have to find the ash, which you have to analyze the white material, if it is ash, pseudomorphs, for example, from the ash. You should have your heated clay. That's what I say. We check carefully the bottom of this, because this fire has been made on a substrate, and we take the substrate as a control, and this should be heated, because 300, 400, 500 degrees, it is recorded by the clay here in the event. If they burnt dung, we should find some phosphate included here. And if it is dung with straw and so on, we should find the phytoliths, the silica skeletons from the plants. So if you have all these included in this context, then you can build the confidence that this is in situ. So independently that here I have my jar or the pottery, but I know that this level, which is related in the stratigraphy with another one, or with the room, or there is a previous excavation that is related to, then I know that this date is a terminus post quem for everything is above, and is a terminus ante quem for everything is below. And I know that this level is this date. So when we are looking for high density sampling, we look also for this type of context, not only the silos or the seeds inside the jar or the fireplace, and very evident, but really for all these small events that can give us more material for dating. How we do that is because we bring our lab, not the accelerator, of course, but we bring the infrared spectrometer, we bring a microscope to observe the material, we bring the centrifuge to separate the different components, and we look at that while we are excavating, and so we can immediately go back to the excavation and maybe sampling more or more carefully, or look in more details for that, and refine the question. This is that's why working through the excavation is essential when you have to build a high resolution chronology. In the lab, then of course we continue, because then later on we collect more materials, and then we look more in details. We try different things with our instrumentation, and the major one is definitely the infrared spectrometer, because it gives us the mineralogy, give us the material, the chemistry of the material we are looking for. We don't have to guess if it is white, if it is phytolith, if it is a silica or calcium carbonate or ash. And with a microscope, we can check, you see the pseudomorph, if they are present in the ash, then we know it is ash and is calcium carbonate. We can look at the phytolith, isolate, and you put it on a slide, and you see immediately the skeleton. Then you build up your context for the C14. The infrared, which is an analysis based on the interaction of light with the molecules inside your material, give you what we call it a spectrum. Here you have the energy of the light, which is absorbed by the different molecule, because each specific molecule, if it is calcium carbonate or silica SiO2, or if it is a phosphate or I don't know, gypsum and so on, will absorb at different frequency light. And the peak that we see here give us the identity of this molecule. For example, here we have the identity of the clay. This is just a natural clay. We have the OH of the water peaks. We have the major peak at 1032 here, and the 530 is a silica. Here we have the doublet of the SiO2. So this is just when we see the spectrum, we know we have just clay, natural clay. And for example, if you start heating the clay at 400 degrees, at 500 degrees, 600, 700, and so on and so forth, you see that your, for example, these two peaks disappeared. At 500 degrees, you don't have those peaks. So if your clay doesn't show these two peaks, then you understand that you are in the presence of temperature. Your clay has seen the temperature. The peak, you see the 530 peak, as you heat at 600, disappeared. This vibration of the molecule disappeared, and you have the evidence that you probably are above 500 degrees. And when you see you're at 1032 peak, the major one, moving, okay, to 1041, 48, 87, then you see that the temperature goes up. And this is what these are the methods that we develop with the infrared, detecting temperature in your sediments. You can also calcium carbonate. You can detect if your calcium carbonate is geological, like limestone, chalk, or if it is a calcium carbonate from plaster or ash. You have the crystal order disorder of this material, which is detected by the infrared, and we also build this methodology. So then you have all these evidence, and you can definitely search for more context for your chronology. So once we have this, as I say, then we have to resolve the problem of the contamination into the sample with the chemistry, and then you prepare your sample for the 1 milligram of carbon graphite, and this 1 milligram is introduced in the ion source of the accelerator, and we measure the C14 and then calculate the age. As you see, the process is very big, very long. But what goes here in the ion source is, when I say is the moment of no return, because if you didn't check carefully your context in the field, and you have your sample strictly related to your event, and you didn't check the chemistry carefully, the accelerator can be the best machine in the world. It will definitely measure all the C14 in your samples, but this C14 will be part from the contamination, and maybe your sample maybe moved through the layers and you didn't see, or it was through the flotation, maybe get more humic when it is wet and then dry. So all this is, this measurement can be as precise and accurate by the accelerator, but if this step is wrong, the chemistry or your context is wrong, then there is nothing you can do. The C14 determination will not be useful for your interpretation. So that's why when I work for the chronology, in this case, I do work first in the field. That's the first lab I really stress, because if that's wrong, then everything else, the chemistry can be perfect, the accelerator can be perfect, but if your context is wrong, then it is not useful in the research. So for the last half an hour, I give you an example. Now I wrap up everything. For the Jerusalem project, we've been working for the last 5 years to rebuild the chronology of Jerusalem. We got an ISF from the Israel Science Foundation, and has been working with many archaeologists because there is a huge number of sites in Jerusalem. And when we started this project, there were maybe less than 10 radiocarbon measurements in the whole area of Jerusalem. Today, after this one, I think we are very much closer to about 1,000 measurements. This is only some of the sites that we have been investigating, and you see this is the Temple Mount location. So we have been excavating under the Wilson Arch and Gihon and all these sites, which are part of a large program to build for tourism, you know, to make it more accessible to tourists, all the different archaeological sites. We are going to talk about the Gihon Spring. This has been published in 2017 in Radiocarbon. The Gihon Spring is the tower, is the spring which is perennial and is giving water to Jerusalem. Well, not today, but in the past was the water source of Jerusalem. And there was a tower, the Gihon Spring Tower, that protected that water source. According to previous excavation in the area, this tower was associated to the Middle Bronze Age too, and this was based on pottery or cultural remains that were set in this Middle Bronze Age too. So because of these restoration works for the tourism and so on, this tower, which is here, is this, in this reconstruction of Jerusalem, is here the tower. So it became available, the excavation below the tower, okay? Here is enlarged the tower. So this corner, which is now is not open, and the area, I mean, is open to tourism, but is inside a structure. The tourists can go down and pass by and see the tower that is defending, I mean, including the spring. The tourists can walk in the water and see the structures that was built later on for this. So this is the plan of the tower you see here. This is the tower, and this is the different passage, and these are for the tourists and so on, but also the passage that in the past the people were using to get to the water, collect the water, and so the section that was available for us is here. This is the southern section of the tower, and this would be the northern section of the tower. And this stone is the one that we will see in the different images. So this is the one that kept all the sediments on which the tower was built preserved. So here, having these sediments here under this huge stone still there, gave us the opportunity to sample and try to give at least what we say a terminus postquem, okay, for the building of the tower. We sample in two different locations, in the northern and in the southern, because first of all, we want also to check if the dates would have been in agreement, or what do we understand about the background where the tower was built, because Jerusalem is built in a slope, on a slope, is not a tail at all, as one expects. So here we see you see this is a meter size. So this stone, and this is huge, is more than a meter in size, and these are the sediments. Once you clean and you re-expose, and then you have the sediments available for sampling. So we have clean 20-25 centimeter of the sediments and sample the layers behind those. So every time we saw a change in the structure or in the composition or in the features of the sediments, we subdivided all these in many different layers. We sample also along these identified features. We sample different spots in order to see if the sediments are indeed the same along, like, you know, you try to build if this is just an accumulation of soil, or there is indeed a hidden sequence in that. So we remove 5-10 centimeter. The stratification was identified. Sediments were sampled for microecological analysis, and we went 20 centimeter deep in order to really collect a lot of samples in those 20 centimeters, so that we can maybe recover some more material. Pay attention that we do always dry sieving and not flotation, because flotation is not good for charred remains. There is a chemical reason for that. And then we divided in basket, like, you know, as for the record. So we use basket to identify the units for that. Just to show you the infrared of the different loci that we separate, as you see, they are, you know, for example, this one on the top is burnt. We don't have those water clay peaks. If you see this one as the peak of the calcium carbonate, much smaller than this one, than the clay one. Okay, so these have been reproduced along the layers, so we know that the composition is the same. This one, the yellow one, as you see, it has the peak of the calcium carbonate much higher than the one of the clay. So here, in this yellow one, which we call it yellow because it appears yellow, but apparently is very rich in calcium carbonate and not in clay, as maybe it would have appeared. So having this separation and having also repeated in the horizontal direction, it told us that this is really a sequence of accumulation through time under this large stone that was here. This large stone. This is not just soil that came in randomly, but it is really deposited one on top of the other, and then they build up. They build the tower on the top of this. So this has preserved this sequence of sediment. When we started to date, initially, we date 3 samples just to have an idea where we are. And we obtain, I think this was 1 date and this was 1 date. So it is in the middle Bronze Age, but we still had another half a meter here. So with the archaeologists, we decided, well, you know, this half a meter maybe goes to the 16th century, and we are still in the Middle Bronze. So we try very hard to find also on the top of these MB dates, other dates. So we added more and more dates to that, and to our surprise, here is the calibrated age. This is 1700 BC, and these were the first dates that we obtained. And we wanted to see if we are here or we are here in order to associate in the Middle Bronze the construction of the tower or not. But then as we move up, so we got this data, which is in the LB. And then as we move up higher and higher, we got 3 dates in the 10th century, 9th century BC. So this, you know, this, I mean, altogether, it is in stratigraphic sequence. There is maybe a gap between this and this period that we didn't find any material to date, but the size of this gap in sediments is very limited, but we don't know if it was being removed or not. But the last 3 dates are in the 10th and 9th century. So the tower, when it was built, it was most probably in the Iron Age and not in the Middle Bronze Age. So we thought about the possibility that this is a repair, but having this stratigraphic sequence first is in sequence by the radiocarbon, and also having this different identity of the layers, you know, it's difficult to see that this is a repair and in the Iron Age, and they just preserved the sediments there. So this gave us, because of all the microarchaeology that we have done here and the many samples dated, it gave us the explanation that this is indeed an Iron Age construction. So this is the end of my lecture today, as for the radiocarbon, so that, you know, when you use the high resolution, the microarchaeology method, but when we went there to excavate under the stone, we knew that we want high precision, and we really needed to certify that those sediments are in situ. They were deposited there, and what we dated inside is the date of the deposition. So this is it. And now if there are any questions or